Welcome, wonderful people. This is Mr. Ndabezita. We will be looking at mathematics and 4. This is question paper number 16030164. It was written on the 30th of March 2023. It's an X paper and it was written for 3 hours. 3 hours was allocated for this paper so that you may work on this. Immediately we will go to question 1. And we have the following. In question 1, they say draw the graphs of y equals x2 exponent 3 and y equals minus x2 exponent 3 on the same set of an axis. So in 1.1, they say draw the graph of f at x equals x3 and g at x equals minus x3, and these are the functions that we would like to draw. Now the question is, how do we go about doing this? Now I will start first with the first one. F at x equals x3, and this is a grade 12 cubic function, and somebody might want to apply differential calculus in order to find the stationary points, the points of inflection, because that's exactly what you are being taught in grade 12. So we will try to see that approach, if it would work, and if it doesn't, then we have a problem. So by just looking at this, I can try to find the stationary points by differentiating this once and equating the derivative to 0 and finding the values of x. So I will say f prime of x equals 3x squared. That's of course what you will find. And then from here you will say the derivative is equals to 0, so meaning f prime of x equals to 0. That is to say 3x squared equals 0. So meaning x is equals to 0. So that would be the value, and then the corresponding value, you take that 0. F at 0 equals 0 to exponent 3, which gives you 0. So that would be the turning point or the stationary point. Okay, there seems to be only one, as you can see, because we found only one value of x. If there were 2, 3, and so on, we would have as many as there would be. So for a point of inflection, we will differentiate this the second time. F second prime would be equals to 6x. F second prime is also equals to 0. So that is to say 6x equals to 0, x equals to 0. And f at 0 would also be 0 to exponent 3, which is 0. Now we have a problem with this function. Everything seems to be 0. Now this is highly problematic because we know the shape of a cubic function, but it might be confusing to others. As you try to draw this, you wouldn't know whether you are looking at something like this or whether you are looking at something like this. So it's highly problematic for one to understand and know when everything is 0 which way you should go. So in order to get rid of that confusion, we are not going to use this method. We are just simply going to use a table of values. So for f at x equals x3, we're going to use a table of values because this is the mother graph. So we're just going to use a table of values, x and y. Let's say minus 2, let's say minus 1, 0, 1, and 2. Suppose this is exactly what we have. So we can substitute a value of x giving us minus 8 minus 1, 0, 1 and 8. So these are the corresponding x and y values that we have, and we can see that we're having both positive and negative values, integers, and negative and positive values of integers on the y and the x-axis. Now we can say, okay, all right, and this is for f at x equals x3. Let's try and check for f at x equals minus x3. They seem to be a reflection of one another, and I know that when I reflect along the x-axis, only the value of y changes the sign. So this is exactly what I have, and if I substitute here, whatever that was positive in here becomes negative, and whatever that was negative becomes positive because of the negative sign that you have there. So I would have my 8, my 1, my 0, my minus 1, and my minus 8. This would be the table of values that you would find, and then that's fine. Let me just try to draw the function. This is my x and this is my y. Now on this coordinate system, it is very important that I try to have a correct interval for x and the correct interval for y. So for x, because I have numbers 0, 1, 2, negative 1, and negative 2, I can use an interval of 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and I can have 1, 2, 3, 4, 5, 1, 2, 3, 4, and 5. Good. Oh, sorry. For y, let's use 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. 2, 4, 6, 8, 10. All right. And then from there, what we can do is the following. We can say, okay, when x is minus 2, y is minus 8. When x is minus 1, y is minus 1. Minus 1 might be a value somewhere there. When x is 0, y is 0. When x is 1, y is 1 might be a value somewhere there. And when x is 2, y is 8. Okay, so let us try to look at how the shape would look like. So this would be the shape of the function. This is exactly what you would have. So this is the function y equals x3, and let's look at this one. And I know this is a reflection, but let's see what type of a reflection. When x is minus 2, y is 8. Very good. When x is minus 1, y is 1. Might be a value exactly here. When x is 0, y is 0, that's a point of intersection. When x is 1, y is minus 1, might be a value just in here. And when x is 2, y is minus 8. There it is. Now let us try to join the points. This is what we get. And this is what we get. And this is the function y equals minus x3. Now let us try to look what is happening here. In this, x and y changes to b. X remains the same, but the value of y changes the sign. Very, very important here. X remains the same, the value of y changes the sign. In this one, we have Okay, let's not talk about this one. This is the original one. There it is. And this one, this is a reflection of that along the y-axis. Because when you reflect along the y, only the value, when you reflect along the x, only the value of y changes the sign. So this is a reflection along x. Along x. And let us try to check if that is true. Let's take the coordinate of this one. -2 minus 8 changes to b. The value of x remains the same, but the value of y changes the sign. What is this? This is the reflection along the x-axis where the value of y only changes the sign. And we can see that the value of y changes the sign, the value of y changes the sign, whereas the value of x remains the same. So this is the reflection along the x-axis. Very important that we understand that. Highly important. So this would be the function that you have for 1.1. All right. So if that's how things are, let's go to 1.2. So I'm just going to erase this. And in 1.2, draw the graph of x squared plus y squared equals 25. X squared plus y squared equals 25. And we want to draw that. This is the equation of a circle with a radius of 1. We know that. And in order to draw the graph of a circle, all we need to know is the x and the y intercept whenever it is provided to us in this way. So what we can do, we can say x-intercept y equals to 0, x squared equals 25, x equals plus or minus 5. And the same thing would also transpire for the y-intercept, because for y-intercept x equals to 0, so we can say y squared equals 25, y equals plus or minus 5. And I can go to a coordinate system of x and y. I have x plus or minus 5, so what I can just simply do is to say minus 5. In fact, let me not do this. Let me draw the circle. Suppose it is like this. Y plus or minus 5, positive, negative, x plus or minus 5, negative, and positive. And this is exactly what I have. A circular function where the radius is equals to 1, x squared plus y squared is equals, where the length of, it has a radius of 1. That's exactly what we are saying. Not necessarily looking at that r equals plus or minus 5. If you look into that, but the radius, it's always equals to 5. So what we are saying to say that the radius is always equals to 1, and that is the, because if you calculate it there, you will have your x squared plus y squared equals r squared. So your r squared is 25, but your r is plus or minus 5. But the radius is always equals to a positive number. In this case, your radius will be 5. But we know that this x squared plus y squared equals 25 will always have an amplitude of 1. That's exactly what we are trying to say there. And then when that is fine, we have drawn this. This is what they wanted. They will first check whether this is a circle. You have your plus or minus 5, and then this is exactly what you should draw. When you have drawn this, we are more than fine. We are more than happy with this. Everything seems to be fine. Now in 1.2.1, they say to us, Is this graph x squared plus y squared equals 25 a function or is it a relation? Now, I know that a function is a relationship that exists between x and y, where one value of x is mapped to exactly one corresponding value of y. And this is a one-to-one function. But this one, it's not a function because it fails the vertical line test. For the same value of x, you have different values of y. So this is not a function, this would be a relation. This is not a function, it's a relation. For one value of x, we have two different values of y. 1.2.2 is this graph of x squared plus y squared equals 25 symmetric about the y-axis? Is this graph symmetric about the y-axis? They ask us the question. They want to know whether is it symmetric about the y-axis. Now let's look into this. I can see that, okay, if I look in this fashion, for the same value of x, I have two different values of y, and the same is happening when I try to run the vertical line test. Okay, so they want to know whether the function is symmetric about the y-axis. Right, and then when I look horizontally like this, you can see that for the same value of x, for example, let's stay in here. So you would find for x a corresponding y value, for x a corresponding y value. So is this symmetric about the y-axis? Yes, it is symmetric about the y-axis. Why are we saying this? We are saying that yes, it is symmetric about the y-axis. You remember when we dealt with symmetry? That's exactly what is happening here. It is symmetric about the y-axis because the value here is the same as, if I do this, the value here is the same as the value there. The difference is that here it is positive and there it is negative. So this is symmetry. The same value but symmetric about the y-axis. You're having a y value that is negative and at the same y value that is positive. So this is symmetric about the y-axis. Very much symmetric. So saying the same values of y, you are symmetric about the y-axis. The same value of y, just that the signs are different. Very important. You are symmetric about the y-axis. So this is us saying this is a reflection. A reflection along the x-axis. If you reflect along the x-axis, I know that the value there would be the same as the value in here, but just that it becomes negative because when you reflect along the x-axis, only the value of y changes the sign. So this is symmetry along the y-axis. And I hope that this makes sense. Make a neat sketch of the two functions. They give us the functions y equals log e x and x equals log e 1. They want us to try and maybe draw that, make a neat sketch of those two functions. And the question is, how are we going to do this? Now, I know that I can change log to exponential in order to work with something that I can consume more easily. So this would become e exponent y equals x. We dealt with this many times with my grade 10s when we looked at, with grade 11s when we looked at technical mathematics. in many cases when we solved for x, we used this method, changing logarithmic to exponential and exponential to logarithmic. So you might want to go and look at those tutorials in grade 11 technical mathematics. And this one would be ex equals 1. So as you can see, the difference is here. E exponent y equals x, but here E exponent x equals 1. Okay, so I know that when I work with this, I can draw the graph of this. And then I just take the reciprocal values of x and y in order to draw the function of that one. So how do I do that? Now I can just come here. I can use a table of values. I can honestly use a table of values. Now let me just say the following. Now the solution, I'm going to start with this one. I'm going to say ex equals y, and I know for x-intercept y is 0, y-intercept x is 0. Let me start with that. X-intercept y equals to 0, 0 equals ex, okay. And then how do I find the value of x? I can introduce the len on both sides. So I can say len 0 equals len ex. Len 0 would be equals to x len e. Len 0 equals, this is 1, and then your x is equals to the len of 0. Let me just go to my calculator very quickly and see what is the len of 0. The len of 0 does not exist, so no x-intercept. So this is error. So there are no x-intercepts. Let me try to find the y-intercept and see what will transpire. So for y-intercept, x equals to 0. This would be y equals e exponent 0. Anything to exponent 0, the answer is 1. So fortunately, we have the y-intercept at 1. Okay, but now the challenge is, does my function go like this or does my function go like that? That's where the problem arises. So this would encourage you to go and use a table of values. So let's go and draw up a table of values, because this is also the mother graph. So your x and your y. Okay, so let's try and check in this function when I input -2, what value will I find? I'll say e to exponent of -2. This is 0.14, tiny value, 0.14. Let me substitute -1, 0.37, or we can say just 0.4. Okay, and I know anything to exponent 0, the answer is 1. So what is e? What is e to exponent 1? That's 2.7. As an approximate whole number, let's say this is 3. Let's just say it is 3. And then when I substitute 2, that would be 7.4. Right, that's fine. So I know that if I can be able to draw this, I won't be able to draw that one, because I will just take the reciprocal values that I have. So what I can do there is just the following. And as you can see, that I don't have any negative y values there, but I'm just going to draw up a Cartesian plane as you know it. And I'm going to have my interval -1, -2, -3, -4, -5. Sorry, this is positive. I'm sorry. 1, 2, 3, 4, 5, 6, 7, 8. One, 2, 3, 4, 5. Right, when it comes to the y values, what I'm going to do is to check very, very closely. The biggest number is 7, and the smallest number is 0.14, 0.4. So I cannot use an interval of maybe 0.51, 1.52, that's going to consume a lot of space. I'm just going to use 2, 4, 6, 8. That's exactly what I'm going to use. So I'm going to say 2, 4, 6, 8, and 10. And the same thing would happen 2, 4, 6, 8, and 10. So this is my interval. Now, when x is -2, y is 0.1. I know that 0.1 might be a value just as close to 0 as possible. And 0.4 when x is -1 might be a value just a little bit above. And then when x is 0, y is 1, I know that y is 1 might be a value somewhere there. Very good. And when x is 1, y is 3. And when x is 1, y is 3. 3 must be between 2 and 4. There we are. And when x is 2, y is 7. So when x is 2, I don't know whether I'm drawing this correctly, but that's exactly what we have. So how is the shape of our function? So our function would go in like this. Very good. So this would be the shape that we have. This is y equals e exponent x. If we were using a graphing app on our laptop, this could have been a very, very smooth curve, but even here you can see exactly what transpires. What is important is a y-intercept of 1, and then the shape of the graph, and then they will look at some other things that might give you the full mark that is required for this. So this would be the drawing. Now I can draw this one. The function y equals e exponent x equals e exponent of y. I have drawn this one. There it is. Now I need to draw this one. Now x equals this. Okay, so when I input here, y is dependent on x, but in here x is dependent on y. So y becomes the independent variable and then x becomes the dependent variable. Hence I said we are going to swap this. So we're just doing the following. X and y, y and x. Y now becomes the independent variable, and the corresponding values there. 0.14, 0.4, 1, 3, 7.4. Now those becomes the values of x. We are having a problem. Right, that's fine. When y is -2, here it is. X is 0. When y is -2, x is 0.1. 0.1, very, very close to 0. very, very close to 0. Might be a point just in here. When y is minus 1, y is 0.4. So minus 1 can be a value somewhere here, remember, minus 1. So 0.4 can be a value just somewhere in between, very, very close. And then when y is 0, y is 1. Where is it? Exactly here. Okay, now when y is 1, x is 3. So there is my 1, and y should be, x should be 3. 1, and x should be 3 there. Very good. And then when y is 2, y is, when x is 2, just above this, my x is 7.4. So let's say maybe 7.4. Let me do this. I will have my 6, my 7, and my 8. So 7.4, very close to 7.5. We might have a value there. So let's see the shape that we will be having there. So here I am. This should be the function. Can you see that? Very, very good. So this would be x equals e exponent of y. That's exactly the function that you have. And this is symmetry along the line y is equals to x. I would argue, but they never asked anything to do with that. They just said to us that we should make a neat sketch of this. And this is exactly the sketch that we have. And that was the end of question 1. I think I will see you in the next tutorial.